A cargo plane sits idle on the tarmac at dusk. Its belly opens like the hatch of a spacecraft, revealing a refrigerated chamber that will soon cradle one of the most delicate exports of the ocean, Marlin. Behind that serene moment, beneath the mechanical choreography of forklifts and flashing signal lights, lies a challenge no less complex than landing a satellite, transporting living muscle across the sky without letting time or temperature win. Inside these planes, a silent battle unfolds. It's not just cold versus heat. It's a paradox of aerothermal dynamics. The internal temperature of cargo holds doesn't decline in a clean, linear way. Instead, it moves in gradients, peaks, and pockets. Thermal turbulence that ignores the biological clock of the marlin itself. The fish, once majestic and warm-blooded in tropical waters, begins to enter a slow collapse. Not from external heat, but from internal enzymatic decay. And here's the problem. That decay curve doesn't align with the cargo bay's temperature behavior. What looks like refrigeration is often just a slow misunderstanding of biology in motion. To understand how precise this transport must be, picture a hydraulic nozzle on a precision pesticide sprayer. Its calibration must adapt to the weight of each droplet, altering the flow rate with microscopic accuracy. In the same way, transporting marlin demands thermal modulation, tailored not to the container, but to the fish itself. Each fillet has a density, each muscle strip has a fat pattern, and each variation changes the speed at which decay spreads. The cooling isn't just about degrees, it's about anatomical thermodynamics. Engineers face this kind of precision elsewhere, deep in the ocean, inside the hulls of submarines. In those machines, pressure control is everything. A single imbalance between compartments can shift internal climate, stress materials, or compromised navigation. That same logic applies in the sky. A fuselage exposed to jet speed wind and fluctuating altitude creates pressure zones around each marlin, not visible, not audible, but enough to turn a perfectly packaged filly into a high-risk product. And yet, most freight systems don't even register the real metrics. They track surface temperature, external insulation, and crate compliance. But they rarely log the sagittal cut depth of the fish, the vertical line from spine to belly. And that detail alone, barely visible from the outside, determines how oxygen and temperature seep into the muscle. It's a better predictor of spoilage than any foam or plastic wrap. But it doesn't appear on a single freight manifest. So here's the provocation. If a submarine can calculate its buoyancy per cubic liter of hull tension, if a sprayer nozzle adapts flow by micrograms of pressure, why does Marlin air freight still standardize cold distribution by container instead of by anatomical mass? Why does a plane carry tons of high-value protein across hemispheres without adjusting its cooling logic to the biology it's preserving? This isn't a question of refrigeration, it's a question of intelligence. And the answer begins not with a thermostat, but with the muscle memory of a fish, still moving, even after the At cruising altitude above 9,000 meters, a marlin fillet doesn't just endure cold. It undergoes biochemical stress. To the untrained eye, the cargo bay looks like a stable chamber of frost, but inside the sealed vacuum packs, something is accelerating. Proteins begin to fragment. Enzymes that should remain dormant become active, even at temperatures considered safe. The fillet starts to break down. Not because the cold failed, but because pressure and vibration conspired in silence. The culprit is partial oxygen pressure. At altitude, the concentration of gases shifts subtly, and those shifts awaken reactions inside the fish. The ATP reserves, molecules that fuel muscle function, begin to degrade fast. This doesn't just cause softness, it leads to color, change, flavor, alteration, and the first signs of browning along the line. A marlin shipped at sea level can stay firm and bright for 60 hours, but at altitude, that window narrows. Sometimes by 19%. The cold hasn't disappeared. The air has changed, and with it, the behavior of the muscle. That's why a new generation of logistics engineers is no longer thinking in degrees Celsius, but in atmospheric composition. Enter the controlled atmosphere cargo pod, a sealed unit that doesn't just cool, but balances oxygen and carbon dioxide diffusion in real time. These pods reduce the metabolic stress on the muscle. They stretch the freshness curve, not by refrigeration, but by biochemical deceleration. They're less like ice boxes and more like low-oxygen greenhouses tuned for fish tissue. Singaporean exporters were among the first to adopt this logic at scale. After introducing micro-compensation units into their aircraft pallets, devices that adjust internal barometric pressure mid-flight, they saw a 32% reduction in freshness complaints. It wasn't a colder shipment, it was a smarter atmosphere. The fish arrived firmer, cleaner, and with better muscle elasticity, a difference invisible to most eyes, but decisive at the market. This shifts the paradigm. No longer is it enough to map a cold chain by distance, by container count, or by destination. It must be mapped by enzymatic resilience. Different species decay at different speeds. Different loins respond differently to altitude. The question isn't just how cold the journey is, but how alive the muscle still thinks it is. Designing around temperature is no longer enough. Every shipment of Marlin in the sky is a cascade of biochemistry in motion. Every crate is a living cell, reacting, adapting, degrading, resisting. Flight plans must evolve, not to suit airports, but to serve molecules. That's not just logistics. It's physiology at altitude, and it's changing everything about how the world eats fish. Takeoff is not a gentle phase. In the span of seconds, hundreds of crates are pushed backward by acceleration forces, compressed by cargo net tension, and shaken by the flex of the aircraft floor. What looks static in transit is, in reality, a constantly shifting load under invisible stress. For vacuum-packed Marlin, this moment is critical, because under acceleration, the structural integrity of the packaging becomes vulnerable. The internal pressure of the crate shifts. Plastic seals stretch. Micro-punctures form, not from impact, but from uneven deformation that no one sees. The issue is cargo misalignment. Crates are rarely filled with perfect uniformity, and pallet configurations often favor logistical convenience over structural optimization. This results in asymmetrical load distribution. When the plane accelerates, pressure ripples through the packaging like a slow-motion wave. Near the edges, plastic flexes and then relaxes. Near the base, it compresses and holds. In Marlin freight, this leads to puncture zone. Silent failures that allow oxygen in, without any visible warning. One leak, one patch of soft flesh, exposed, and the cold chain is breached before the plane ever levels off. To counter this, engineers have looked not to the seafood industry, but to aerospace logistics. The solution lies in structural load balancers, crate components made from polymeric tension-damping materials, originally developed to protect delicate instruments inside satellites. These materials don't simply absorb impact. They manage force. They redistribute acceleration loads across the crate base, reducing pressure spikes on vulnerable points. The result is a more uniform cargo response and fewer failures. The data confirms the problem. Fillets packed within 40 centimeters of the container floor suffer 11% more leakage due to pressure wave dynamics alone. It isn't a matter of poor packaging, but of physics under strain. The crate does its job until acceleration changes the equation. Some exporters have adapted. In Chile, one logistics company redesigned the entire base of their fish crates using aircraft-grade shock-absorbent polymers. In a single export cycle, their incident rate of vacuum pack breaches dropped by 26%. The crates look the same. The difference was in how they responded to the choreography of flight. The principle is clear. If humans designed seat suspension systems to absorb every phase of turbulence, the same philosophy should apply to fish crates. Model them not as boxes, but as engineered containers undergoing high-velocity transit. Simulate their behavior under G-force before the first Marlin is even loaded. Treat the crate as part of the aircraft, not just cargo, but a system in motion. Because in high-value protein logistics, every vibration counts, every shift matters, every pressure wave is a threat waiting to be engineered. Precision, in its truest form, is not a matter of mass. It is a philosophy of movement. In the world of modern agriculture, we've seen machines that sow seeds with centimeter accuracy on uneven hillsides, that analyze soil density in real time, that adjust row spacing automatically as terrain shifts beneath heavy tires. But there is a new frontier where this same intelligence is being applied, thousands of meters above the ground, in the cargo holds of wide-bodied aircraft flying across oceans. Here, the product is no longer grain or fruit, but flesh, not inert or frozen, but biologically active muscle. Specifically, Marlin, harvested and packed within hours, yet still metabolically ticking as it is loaded into the... To understand what's at stake in this environment, consider what happens when we don't. Traditional cold chain logistics treat all cargo as passive matter, set the temperature, seal the container, and hope the insulation holds. This method might suffice for certain grains or frozen goods, but for Marlin, a species with unique biochemical volatility and a high oxygen sensitivity, this static approach falls short. Muscle fibers, even at refrigerated temperatures, continue to undergo proteolytic changes. Moisture retention decreases, color darkens, texture softens. These are not signs of failure. They are the silent symptoms of time and atmosphere moving faster than the system built to contain them. It is in this context that the cold chain is being reimagined, not as a linear sequence of storage points, but as a responsive ecosystem, one that draws its inspiration as much from aviation engineering as it does from agronomic science. Imagine for a moment a crate of Marlin not as a box of meat, but as a living object, one with spatial variability in water content, fat distribution, muscle tension, and metabolic residue. Now imagine that object flying through layered air masses, subjected to pressure differentials, vibrations, and atmospheric shifts. The question is no longer, how do we keep it cold, but how do we preserve its structural identity? This is where adaptive logistics steps in the same way that hillside planters adjust seed injection angles based on gyroscopic sensors and topographic mapping. Marlin freight now requires micro-adjustments throughout the flight, not just in the cabin temperature, but in crate tilt, airflow direction, vibration dampening, and oxygen concentration. The idea is not to freeze the decay, but to slow its trajectory, to hold the biological clock in suspension, even as the aircraft moves from one continent to another. Some of the most advanced carriers in the world are already applying this mindset. Emirates Sky Cargo, for instance, has incorporated dynamic airflow control algorithms into its seafood logistics protocols. These systems don't merely distribute cold air evenly. They analyze cargo density, estimate surface area exposure, and modulate airflow based on the thermal absorption properties of each shipment. In simpler terms, they calculate how muscle mass retains cold over time and adjust circulation to preserve hydration at the microscopic level. The goal is not just temperature control, but water retention, texture stability, and aesthetic integrity, qualities that determine whether a filler reaches the market as premium grade or downgraded stock. But the technical challenge is only half the story. What truly changes here is the mindset. For decades, logistics treated food as a substance to be protected from heat. Now it must be seen as a biological narrative in progress, one with time-sensitive chapters that unfold even under refrigeration. A Marlin fillet at 2 degrees Celsius is still undergoing change. Its story isn't paused, it's just slowed. And that awareness must guide every mechanical decision along its path. This reconceptualization requires us to go back to first principle, to rethink what we're moving, why it matters, and how it behaves in transit. Just as no farmer would irrigate all fields identically without assessing soil structure, No freight planner should design seafood logistics without mapping the biological terrain of the cargo. Every mussel has a pattern, every pattern has a decay rate, and every rate demands a unique logistical response. That is the invisible future of agro-logistics, one where agricultural mechanics extend seamlessly into the air, where smart crates behave like living chambers, and where freight is not simply transported, but managed with the same finesse as a planting schedule or a harvesting circuit. A crate becomes an aircraft component, a flight becomes a preservation strategy, and every decision, from packaging material to atmospheric programming, becomes an agricultural act. In the end, this is what connects the field to the flight. The same intelligence that guides a planter along a sloped ridge now guides a marlin across hemispheres. Quietly, precisely, elegantly. Not for show, not for spectacle, but for... Because between the ocean and the plate, there exists an entire chain of human ingenuity designed to protect something that breathes, decays, and nourishes. If this journey made you see logistics differently, take one more step. Check the pinned comment. It might just lead you somewhere you didn't expect.